where I compare, like we talk about rolling different round objects down a hill and do the calculations for what's going to go faster. And I want to do pulleys with mass. I think that's a pretty interesting one because it's probably occurred to you several times before, like, what if, what if the mass does matter? Well, now we can finally do that. Before I do that, anybody have any questions about the test?
So,
Okay.
so if it's a particle, you don't treat it as if it has mass to it.
No, you do.
Oh, it said it had mass. I know, but the gravitational force.
Oh, so if anything, I was pretty relaxed about including weight, but well, we can look at it later. But yeah, that I think my guess is there was something else that I saw that was going on, but I can look at it later. But if something asks for F net, F net lumps everything together. So then all you do is multiply the mass times the acceleration. Newton's second law says F net is equal to mass times the acceleration of the center of mass. So if you know the acceleration of the center of mass, F net, just multiply the mass. Okay. Okay. Yeah. Yes. Yeah, I know. So let's do an example. Round objects. Rolling down a ramp. And we're going to use what we know about rolling without slipping. And that is that if you choose a coordinate system, so there's the ramp, it's some angle. If you choose a coordinate system with the y-axis pointing out and the x-axis along the incline, then we know that the velocity vector of the center of the round thing is equal to the x component negative omega r, y component 0. And the acceleration of the center has the x component negative alpha r, y component 0. Okay, so we talked about that with kinematics. Now we're going to include the loads acting on these things. And I'm just going to do this problem for a general thing with a round outer surface. So we'll assume that the mass moment of inertia about the center is I COM. No, actually that's a mistake. I center. Okay, so C is the center of the round shape. It's not necessarily the center of mass. Like for example, if you had, you don't have to draw this, but if you had this round shape like this and removed a square of material from it, the center of that circle does not match up with the center of mass. Okay, so I want to leave that option open. All right, so we're just going to go through the steps for rigid body kinetics problem. Okay, so the first step is we have to decide, so we have an object rolling down this incline. So it's going to be moving this way in the positive x direction. Its angular velocity and angular acceleration are going to be counterclockwise, clockwise. The first step for a rigid body problem is you have to decide whether there's a fixed point or whether we have to use the center of mass as the about point. So if something's rolling, this is sort of an interesting, like, there's a little subtle thing to this. And that is that the point that's in contact with the ground has zero velocity at that instant, remember? But it doesn't have zero acceleration. There's a centripetal acceleration pointing toward the center. So the velocity might make you think that we're going to assume that that contact point is a fixed point, but the fact that there's acceleration says we can't make that assumption. Okay, so there's no fixed point, and we have to use the center as, oh, well, we have to use the center of mass as the, so no fixed point. So the about point is the center of mass. As long as, so anytime something's rolling without slipping, the velocity part that's, so the velocity has to be zero at the point that's in contact with the surface. And the part of the acceleration that's parallel to the surface has to be zero. Yeah, but it's kind of not tangential acceleration because it's a relative motion problem. That is the term where it comes from, yeah. So it's not exactly like in circular motion because the center is translating to, you know. That's right, yep. So second, the second step is we find the mass moment of inertia. That to us is just ICOM. And now I'm changing my mind again about this. Let's call this ICOM. You can just write an O and an M after the C. Yeah, right, exactly. Don't let it happen again. And then the third thing, I guess that must be free body diagram and stuff. Yes. I don't really remember. I'm just trying to remember what order I would sensibly put down as an order of things. All right, so free body diagram. Here's our object. Well, you can go in any order. You can go in any order you want as long as you do all the stuff. I listed the steps in an order because I thought it might help you remember. So shut the fuck up. Okay, so there's the weight. I'll just call that the mass is mg. And then here's the contact point. So what loads are acting at that contact point? There's definitely a normal force. Well, so that's the right way to think about it. There is a friction force because it's not slipping. If there wasn't a friction force, it would just slide down, you know. it wouldn't rotate at all. So that friction force is what makes it turn, and that has to be acting in this direction, parallel to the surface. And I'll just call that FF. Any other forces? That's it. And so row force moment. Okay, so the row vector goes from the about point to where the force is applied. This is the about point because it didn't have a fixed point. And so first for the weight, the row vector is 0. Since we're using this skewed rotated coordinate system, we have to represent that weight force, using sine and cosine. We need to give this an angle. Let's just call it theta so it's general. And so this force vector is going to be mg, positive mg times the sine of theta. And the y component is going to be negative mg cosine theta. And there's no moment. Then the normal force. What's the row vector from the about point to where that normal force is applied? 0, negative r, yep. And the force vector is 0, positive n, 0. And so the cross product between those is 0 again. And then the friction force, that's at the same location, so it has the same row vector. But that force is in the negative x direction, so negative F, 0, 0. And the moment is 0, 0, negative RFF. Okay, so next, we sometimes use Newton's second law. We sometimes don't. Do we have to in this case? We do because there's no fixed point. We can skip it at this step if there is a fixed point. Okay, so Newton's second law says mg sine theta, negative mg cosine theta, plus 0n plus negative FF0 is equal to the mass times the acceleration. For now, I'm just going to call this mass times, we know that the acceleration is going to be parallel to the x-axis, so I'm just going to call this AC0. Finding that normal force isn't getting us closer to what we're trying to find is the acceleration of the center. Finding that normal force doesn't help at all. That's unrelated to the acceleration. So I'm just going to use the x equation. And it says negative FF minus MAC is equal to negative MG sine theta. And I broke it down like that because AC and FF are variables. These other things are parameters. We're assuming that going into the problem, we would know what M is. G obviously is a constant. We would know what theta is. So we're trying to find everything in terms of M and theta. And I'll just set this aside. We can't solve that equation yet because we have two unknowns in one equation.
So as soon as that circle hits the bottom of the incline, we can no longer say it's only moving in the acceleration.
Right, but then that's right. We're assuming a fixed angle, like a constant ramp, anyways. So, okay, and then 5 is rotational equation. And that says if we only look at the z components, negative RFF is equal to the mass moment of inertia about the center of mass times alpha. Okay, so, well, let me rewrite that. So, negative RFF minus I for the center of mass times alpha is equal to 0. That's our second equation. But the problem is we added a new equation, but we also added a new variable, alpha. So now we have two equations, three variables. What do you think is the last step here? Well, actually, in this case, that's a good thought, but that's not going to help us in this case. So now we're going to come up with a constraint equation that relates the acceleration of the center of mass to that angular acceleration. So, yeah, that's what we're going to use. Yep. So here we have two equations for three variables. And so our constraint equation says AC is equal to negative alpha R. Which is equivalent to saying that alpha is equal to negative AC over R. So now we can decide which one of those two we solve for. We're looking for an acceleration of the center of mass, so I might as well substitute an expression using AC in for anything that has alpha. Okay, so let's rewrite these two equations. So our system of equations says negative FF minus MAC is equal to negative mg sine theta. And our second equation says negative RFF minus ICOM times alpha, but I'm going to substitute this in instead. So plus ICOM over R times AC is equal to 0. And if we're trying to solve this system, we can take the first one and subtract the second one. Let me just rewrite these again. So I'm going to multiply the first one times R. I'm going to multiply the second one times negative 1. And we get negative RFF minus RM AC is equal to negative MG let's say RMG, negative RMG times sine theta. And then the second equation, we're just taking the opposite of that one. So we have positive RFF minus ICOM over R times AC is equal to 0. And then we can just add these two equations together. I'm just solving this system. You can do it however you want, substitution, or your calculator will do it with reduced row echelon form. But so we end up with negative RM AC minus ICOM over R times AC is equal to negative RMG sine theta. And so I'll write this as AC is equal to RMG sine theta divided by the quantity RM plus ICOM over R. Okay, so this gives us an expression for the acceleration of the center of mass that depends on the mass moment of inertia, the radius, and the mass, and the angle. To make a little more sense out of it, let's think of the mass moment of inertias for a few of the round shapes that we've dealt with. So ICOM for a disk was equal to 1/2 times the mass times R squared. For a sphere, was, I think, 2/5 times the mass times R squared. So let's think of we'll use a somewhat general mass moment of inertia about the center of mass of a constant times the mass times the radius squared. Then our expression for the acceleration of the center is, so we still have all this stuff on top, r mg sine theta. And on the bottom, we have rm plus ICOM, we're going to call CMR squared, and we're dividing by r. So that's just going to be CMR. We can cancel these r's and cancel these m's. And what we get is that the acceleration of the center of mass is equal to g sine theta divided by 1 plus c. Okay, so if you increase the denominator, you decrease the acceleration, right? That's and so go up here for a disk. The value of that constant c is 0.5. For a sphere, it's 0.4. So you're going to get a smaller acceleration of the center of mass for a disk than you are for a sphere. So a sphere accelerates less than a disk. No, I said it backwards. Damn it. Okay. Well, it's due to the fact that, like, if you think of the way mass is arranged around the center of mass, a sphere, because it bulges out in the direction that we're not looking at, manages to get a lot more of its mass close to the center of mass than a disk does. Like, the disk has this uniform distribution of mass at every different radius. Right. Yeah. That's right. It would accelerate really slowly. Right. Right. I don't think probably, but I don't know.
It's actually liquid.
Okay, so what else does this say? It says, like, there's a couple surprising things. The first one is one, I mean, you would believe they would accelerate differently, a disk and a sphere, but you wouldn't, off the top of your head, probably guess which one would go faster. But a sphere will always get to the bottom of this hill faster than a disk will. Notice that all the dependence on the radius and the mass cancel out. That's weird, So, like, a gigantic sphere will still accelerate down the hill faster than a dime or whatever, We're ignoring air resistance, totally. Yeah, so. Well, We didn't talk anything in this about the speed that anything's moving, right? So at the start of the motion, air resistance wouldn't make any difference at all because air resistance force depends on the speed squared. So at the start, when you have zero speed and just an acceleration, you'd get basically perfect, agreement. As the thing started to speed up, the importance of air resistance would increase, and it increases as the square of the speed. So the dependence goes up fast, Yeah, well, we didn't say anything about the thickness of the disc. So this also holds for a cylinder, a long, like rolling a pencil down an incline. If you're thinking of it in 2D, a pencil is a disc, But yeah, this doesn't take any air resistance into account. Okay, what about a hollow disc, like what am I thinking of? A ring, or a cylindrical hollow tube. Well, coming up with the formula for the mass moment of inertia for a ring is not horribly complicated. It's a little bit complicated. It takes half a page. And you get a result that looks a little counterintuitive, but the mass moment of inertia about the center of mass of a ring is 1/2 times the mass times the outer radius squared plus the inner radius squared. You'd probably on first thought think that you'd be subtracting the inner radius squared, but it gets complicated because this would be minus if you were starting with a solid disk that had mass m, and then you removed material from it, but then you'd end up with a mass that's less than this m, and so all this algebra comes in, stuff cancels out, and you get that formula. Eric, do you have a question? You can't. It's exactly the same. So this formula works for a hollow tube too. And so to get the value of that constant C for a ring, you just have to know what the ratio is between these. Okay, this is your R, and so if you say like the inner radius is half of the outer radius or something, then you'd have something that said 1r squared plus 0.25 r squared. Pull that out, you'd have 1.25 over 2, and 1.25 over 2 would be your, 0.0625 would be your constant C, and that's what you'd be comparing to those other two. And so the more the material is spread out to the outside, the slower it's gonna. Yep. Yeah, this is all barbette related. The thinner that's a good idea. That would probably get a lot more people enrolled. Same number of people finishing though. The thinner the ring. Yeah, the thinner the ring, the less acceleration. Yeah, that is. Yeah, smart.